classification of representations of orthogonal and symplectic groups. So it opens up the natural question about how these two descriptions compare. In 22, Cunningham, Fiori, Mrachek, Moussaoui, and Zhu computed and defined the ABV packets using a normalized version of the vanishing cycles functor following ABV suggestions. And of the few hundred pages of examples they computed, they all seem to match what local Arthur packets were understood at the time. So that sort of gives us a geometric version of a local Arthur packet, which we call ABV packets, Adams, Barbash, and Vogan packets. And these are the proposed geometric analogues. So the main problem for today, which is stated imprecisely here in the beginning, is that an ABV packet defined for a Langlands parameter of Arthur type matches the local Arthur packet for the Arthur parameter. And this is a project in collaboration with Cunningham, Hazeltine, Liu, Lowe, and Zhu. And this is one of the results for this project in progress. So today we will be looking at split SO2n+1. So later on in the slide, I'll give a more detailed version of the main result, but roughly we want to show that ABV packets are, Arthur packets are ABV packets. Okay, so here we go. We set up our the main objects here. So F is always a non-Archimedean local field of characteristic 0. G, so this theory is for any connected reductive quasi-split group over F, but for us, we can pretend throughout that G is split SO2n+1. So let's define exactly what that is. So theta is an automorphism of GLN, and it takes X to a conjugate of its transpose inverse. And we take the conjugate with respect to this matrix with plus and minus ones on the anti-diagonal. And SO2n+1 can be thought of as determinant 1 matrices that are the fix of this automorphism in GL2n. When we talk about dual groups, sp2n shows up. So sp2n is the fix of this automorphism in GL2n. And another group that will show up is our disconnected group, GLN times Z mod 2Z. So that's right here. Z mod 2Z is the group generated by this theta. Okay, so in order to talk about geometric versions for a local Arthur packet, we should set up the geometric perspective on the local Langlands correspondence. So that is how we will begin. So I'm sure most people know, but local Langlands correspondence gives us a conjectural many-to-one map between the set of smooth irreducible representations of the F points of G, modular equivalence, to the set of G hat conjugacy classes of Langlands parameters. Here, our Langlands parameters are mapped from the way group times SL2C to the L group of G. And the fiber of this map is a set of representations called an L packet. So this is a theorem for SO2n+1. Now, there are several ways of upgrading this many-to-one map to a bijection. And one of the ways of enhancing them, which Vogan adapts, is which Vogan uses, is the following. So for every Langlands parameter, we can define a component group, which is take the component group for the centralizer in G hat of phi. So if you enhance the Langlands parameters by adding the irreducible representations of this component group, then you can have a bijection. But on the left-hand side, we have to enlarge the set of smooth irreducible representations of G to include new groups, which we call pure inoforms, and they are indexed by H1FG. So now we have a one-to-one correspondence between smooth irreducible representations attached to G delta and these enhanced Langlands parameters phi, rho. And this is the notation for including smoothly reducible representations of G delta. So when you see a pure, we are including G deltas. So our group is SO2n plus 1. So that is always, H1 is always Z mod 2Z. So there is one extra group hanging around. So in order to set up the geometric perspective, we must fix an infinitesimal parameter. So let's define that. So given a Langlands parameter phi, and this is also where we set up this notation, WF prime is Way group times one copy of SL2C. So a Langlands parameter is this map from Way group times SL2C to the L group of G. You can write down its infinitesimal parameter, which is a map from the Way group to the L group of G, as follows. You take the parameter and you substitute this SL2 matrix in the second argument. So this is one way of restricting our attention to just the Way group. And the map phi to lambda is a surjective map. So to write down the Langlands geometric perspective, we always fix a lambda. And once we fix a lambda, we can talk about the space associated with lambda. So what's that space? So this is V lambda, Vogel variety, which consists of all the elements inside the Lie algebra of G hat, such that the add action of the image of lambda on X just scales X by the absolute value of W. So this is our space of Langlands parameters. Each point in this variety is a Langlands parameter. This carries an action of the centralizer group H lambda. So this is just the centralizer of the image of lambda inside G hat. And H lambda acts on V lambda. If you think of them as matrices, this is just conjugation. And under this action of H lambda, our variety is stratified into finitely many orbits. And for us, for our case, V lambda always turns out to be an affine variety. So as I mentioned, each point in the Vogel variety is a Langlands parameter. Each orbit inside the Vogel variety is a conjugacy class of a Langlands parameter. So we have a bijection between conjugacy classes of Langlands parameters that share the infinitesimal parameter lambda and H lambda orbits C in V lambda. So you will see a phi sitting as a subscript of C, which means you're identifying the orbit with the parameter. But there's more. On each C phi, you can write down finitely many up to equivalence nice sheaves, so locally constant sheaves on each orbit. And the equivalence classes of those sheaves are parametrized by this equivariant fundamental group attached to the orbit. And that is just the component group of a chosen base point X phi inside C phi. And you take the centralizer of that in H lambda, and you take the component group. Now, these nice sheaves, these local systems, can be upgraded by taking the intersection cohomology complex to a perverse sheaf. So IC of LC phi is the perverse sheaf attached to the orbit C phi. Okay, and these perverse sheaves are our geometric counterparts to representations. So we put them in a set. We put them in the set. Perverse sheaves, H lambda equivariant on V lambda. The simple objects are given by IC of LC phi. L varies over all local systems on an orbit C phi. C phi varies over orbits in the Vogel variety. So now we can actually write down Vogel's geometric perspective on the local Langlands correspondence. So remember, we have fixed lambda, and we take all the enhanced Langlands parameters so that the Langlands parameters share the same infinitesimal parameter lambda. So that's phi lambda. On the left-hand side, we take via the local Langlands correspondence all of the representations corresponding to those enhanced Langlands parameters. So when I say a representation with infinitesimal parameter lambda, I mean the representation whose Langlands parameter has the infinitesimal parameter lambda. And they correspond to simple objects in the category of equivariant perverse sheaves on V lambda. So pi goes to phi comma L. L is a local system on Z phi, and you upgrade it to the perverse sheaf. And this happens because of this really wonderful identification between the component group we started with, A phi, that gave us the enhancement of the local Langlands correspondence, and the equivariant fundamental group that gave us all of the local systems on each orbit. And because of this identification, we are able to put this together.
What is pi lambda pure?
Pure just means that we are including all of the pure inner forms. So pi lambda G pure is going to be a union, yes, of pi lambda G deltas. Okay. All right. So let's look at an example. So this is the smallest example could legally get away with, SO3. So it's the lambda for SO3. So in place of LG, I've just written the complex dual group, which is sp2c. So if you take lambda to be just this nice matrix inside SL2, the V lambda is the affine line, complex line, and H lambda is the multiplicative group, so torus inside SL2C again. And if you take this matrix and conjugate it with this matrix, then you can easily write down the action, which takes x here to t squared x. So because you're scaling x by some number, there are two orbits. One is when x equals 0, and one is when x non-zero. We get the whole punctured line. So those will be the two orbits. C0 is the origin, and C1 is the complex numbers minus the origin. So we can compute the component groups attached to both orbits, which will give us all the local systems. So the component group attached to C0 is just trivial. So it's irreducible representations. That's the hat over here, is just a set of one element. And C1, because of the t squared action, has component group Z mod 2Z, whose irreducible representations are the trivial and the sign character. Okay, so we can write down the entire correspondence between representations, enhanced Langlands parameters, and perverse sheaves. Instead of writing perverse sheaves, I've just written local systems here. So on C0, there's only the trivial character. So there's only the constant sheaf on C0, which corresponds to this reducible Langlands parameter, which corresponds to the representation pi 0. And I think this is the trivial representation. And on C1, there are two characters. So they correspond to two sheaves. One is the constant sheaf, the other is the square root sheaf. The Langlands parameter is x for both of them. And one corresponds to pi 1 plus, and one corresponds to pi 1 minus. And the row in blue is the other group that shows up. So the row in blue is the pure version. And this other group turns out to be coming from the quaternions. Okay, so let's move on. Instead of thinking about bijection between sets, it is useful for us to think about a pairing between Grothendieck groups. So we'll briefly mention what that is. So Grothendieck group attached to pi lambda pure is just the span, the Z span of the elements in this set. So this Grothendieck group has another basis, which consists of standard modules attached to the irreducible representations. So that is this basis. So the standard module will have pi as the unique irreducible quotient, and that gives another basis. So this is a Grothendieck group on the representation theory side. We can write down a Grothendieck group on the geometry side. as well. So you take the span of all simple perverse sheaves that show up on the geometric side of the correspondence, or you can take the span of sheaves, which are extensions by 0 of the local systems we get on each orbit. So this gives an alternate basis of standard objects. And excuse me, how do we identify these two Grothendieck groups? By using a very nice pairing, which is determined by Vogan's geometric perspective on the local Langlands correspondence. So here I should have changed scalars to C. So just think of them now as vector spaces over C. That's why there's a C here. So pi is identified with P if they were identified with each other under the original correspondence. So that gives us something non-zero, and it's 0 if they were not identified under the local Langlands correspondence. So what is this non-zero? It's a signs plus or minus 1. It depends on the pure inner form that pi came from. So if pi was a representation of the split SO2n plus 1, then this E of delta pi would just be 1. And minus 1 for the other guy. So a nice thing about these Grothendieck groups is that we can start working with formal linear combinations of representations, and we will call them virtual representations. Okay, so remember that we had two bases for these Grothendieck groups, and I have written this pairing down in terms of one basis of simple objects. So how can one describe the aforementioned pairing with respect to the other bases once you fix this for simple objects? And that is the subject of the p-adic version of the Kazhdan-Lusztig hypothesis. So if we fix this pairing for simple objects, then if the p-adic Kazhdan-Lusztig hypothesis holds, then the pairing for standard objects should be this. So the standard representation attached to pi will match with the standard sheaf attached to C if and only if they corresponded to each other under the previously mentioned local Langlands correspondence. And this time we will not see the dimension of the orbit. It's just the Kottwitz sign appearing here. And if they're not identified, then it's 0. So for example, for GLN, this would be either 1 or 0 because GLN does not have any other pure inner forms. For SO2n plus, for split SO2n plus 1, this would be 1, and for the pure inner form, it would be minus 1. Okay, so in the original statement of the theorem, we have a hypothesis which says, assuming the twisted version of the p-adic Kazhdan-Lusztig hypothesis. So by that, we mean that this pairing, when G is replaced by this particular disconnected group. So just a few words about this. So when G is replaced by GL2n semi-direct Z mod 2Z, you can write down a local Langlands correspondence and its geometric perspective using Tarsho-Kaleta's work. And that will help us define this pairing in a similar way in terms of simple objects. And if someone proves the twisted p-adic Kazhdan-Lusztig hypothesis, we will be able to conclude what it is on the basis of standard objects for GL2n semi-direct Z mod 2Z. And so that is what we would mean by twisted PKLH in this case. Okay, and I will say more words about how it shows up in our proof later. Okay, so that was the geometric perspective. It gave us a pairing between Grothendieck groups, and it gave us the ability to work with formal linear combinations of representations. So, yeah. Yes, so p-adic Kazhdan-Lusztig hypothesis will allow us to get the pairing between standard objects for, in this case, a connected reductive group G, if we define the local Langlands correspondence for that. For twisted, we will use twisted p-adic Kazhdan-Lusztig hypothesis to draw the same conclusion for GLN semi-direct Z mod 2Z. So the twist is by theta, so that's what we mean by twisted. The statement for us is that given the pairing in terms of simple objects, which is this, the pairing in terms of standard objects is this. And for GL2N, there will be no quadruplet sign. So it's either 1 or 0. Yes. It's not known. No. It's not known. Yeah. So that would be the hypothesis. Yeah. So that's part of the hypothesis of our theorem as well. Okay, so local Arthur packets. So for that, we need an Arthur parameter, which is a map from the way group times 2 copies of SL2C. And here the notation double prime means there are 2 SL2Cs over here. It defines an Arthur packet, which is a set of representations, unitary representations of G. And given an Arthur packet and a element S in the centralizer in the image of psi, you can write down a virtual representation attached to the Arthur packet, which will be our way of writing the distributions attached to Arthur packet. We write them in terms of virtual representations. And what are they? They are formal linear combinations of the elements inside the Arthur packet, and these coefficients are specified by Arthur. So just wanted to give a brief glimpse of Arthur's theory for SO2n plus 1. So psi is an Arthur parameter, S is a semi-simple element, and eta psi S is our virtual representations. Arthur defines his packet so that the virtual representations are compatible with endoscopic and twisted endoscopic transfer. So the twisted endoscopic transfer version is as follows. When S is 1, you can think of, so the Arthur parameter sits inside, for let's say for our case, SO2n plus 1 sits inside the dual group of G, which can be included inside GL2N to give an Arthur parameter for GLN. This parameter for GLN will give us an Arthur packet for GLN, which is singleton. That is known. And Arthur defines the transfer map from G to the theta component of GL2N semi-direct Z mod 2Z so that eta psi transfers to pi tilde, where pi tilde is a chosen extension of the representation of G to the theta component of the representation of GLN to the theta component of GLN. So basically, our dist virtual representation when S equals 1 should satisfy this equation. And when S is not equal to 1, you can write down the group G prime, or the endoscopic group G prime, so that our Arthur parameter factors through G prime. So G prime is given by the centralizer in G hat of S. So you can write down the Arthur parameter to be a composition of these two maps. And in this case, Arthur defines a transfer map from G prime quasi-split to G so that eta psi prime attached to G prime transfers to eta psi S. So this is the way Arthur packets are defined so that we satisfy these two equations with respect to these twisted endoscopic transfer and transfer maps, endoscopic transfer maps. Okay, so what were the Arthur packets for the example that we saw? So both the orbits actually correspond to Arthur parameters, but if we set our Arthur parameter to be wxy goes to just x, then the Arthur parameter attached to psi is going to be pi1 plus over here. And I did not define it. We deliberately swept it under the rug. But if you wanted to write down a pure version, then that would include pi1 minus as well for this parameter. Yes. So pi0 is the trivial representation. Pi1 is the analog for the Steinberg representation for GL2. And pi1 minus is the trivial representation for D cross mod F cross, the new group that showed up. Okay. So now let's set up the geometric versions, the proposed geometric versions of local Arthur packets. So due to Adams, Barbash, and Vogan, so we must fix the following. So we always start with an Arthur parameter for our talk today, although ABV packets can be defined for any Langlands parameter. An Arthur parameter corresponds to a Langlands parameter in the following way. You plug in this matrix in the third argument of psi. And given a Langlands parameter, we can write down its infinitesimal parameter by plugging in the same matrix in the second argument of psi. So an Arthur parameter psi will fix an infinitesimal parameter lambda in this way. So Cunningham, Fury, Musai, Mrachek, and Xu in the 2022 memoirs book write down this functor that they use to compute ABV packets. So here's the functor. Given an Arthur parameter psi, you can write down its component group, the centralizer of the image of psi in G hat modulo connected component of identity. You can write down its Langlands parameter, which under the geometric perspective on the Langlands correspondence will correspond to an orbit inside the Vogan variety, and we label that orbit as C psi. So now we can define the functor that will help us compute ABV packets. This is a functor from the category of perverse sheaves on V lambda to the category of representations of this finite group. So you take a perverse sheaf, do all of this stuff, and then you get a representation of A psi. In practice, they actually use a normalized version of this functor. So the normalization is simply you take the image and tensor it with the contragradient representation that you get after computing the functor on the constant sheaf attached to C psi. So this normalization is so that the trivial representation of A psi matches with the right thing. So people seem very excited to understand what all of these components are. So let's do that. Because I have displayed it, I thought I might give a glimpse of what goes into it, but it can be a very notation heavy slide. So if you don't like it, you can look at this Monstera leaf unfurling, which is very beautiful. So what was C psi? C psi was our orbit corresponding to the Langlands parameter phi sub psi. You can write down a dual of the orbit C psi inside the dual Vogan variety, which is C psi star. That is called the Piasecki dual. There is a point x psi comma y psi that shows up. We take stocks here. And in general, they must satisfy some nice conditions in the conormal bundle to the orbit. But in this case, it's automatic because we are in the Arthur case. So we will not say anything about that. So x psi is a point inside C and y is a point inside C psi star and is determined by psi. The codimension is the dimension of the orbit of the variety minus the orbit. And this f, the function f psi, is given by the Killing form. So it's a function on V lambda cross C psi star, two complex numbers, and it takes xy to what we get from the Killing form, because V lambda and V lambda star both sit inside the Lie algebra of G. Yes?
So there's another function with the same force target.
I do not know, but maybe there are other experts who might know this. And this is the vanishing cycles functor with respect to the function f psi, which roughly goes from the derived category of V lambda to the derived category of the zero set of f. So you have a complex, you apply the vanishing cycles functor, you get another complex. You take the stocks, you get a complex of vector spaces with a group action. You take the cohomology at a specific degree, you get a vector space with a group action. In other words, a representation of A psi. All right. So now we can define ABV packets and the virtual representation attached to an ABV packet. So an ABV packet for phi psi, so phi psi will give us an infinitesimal parameter lambda. So that's the lambda here. You take all of the representations that share the infinitesimal parameter lambda, you apply the EVS psi functor on the perverse sheaf that corresponds to that representation. If it is non-zero, you collect it inside the ABV packet. And just like in the Arthur case, we write down this virtual representation for any semi-simple S in the centralizer of psi is a linear combination of representations inside the ABV packet. But now the coefficients are given by the NEVS functor. So they are calculated by computing the NEVS functor. You get a representation of A psi. You take the trace of that representation at the element S, and you get the coefficients. So these ABV packets, they appeared in the 1992 work by ABV. Also, Vaughan and then CFMMX used this particular normalized vanishing cycles to compute that. So we can also write down a pure version of these packets and virtual representations. And for the pure virtual representation, the Kottwitz sign also shows up in the coefficients. Okay, so the example that we had originally seen, here are the ABV packets and the pure ABV packets. And the slide is long gone, but if you will believe me, they are the same as the local Arthur packets that we saw in the previous slide. Okay, so now we are able to outline our main goal. And the main goal, as you may have seen, as you may have guessed, is that we want to compare ABV packets and Arthur packets and show that they are the same. And that involves comparing the virtual representations attached to them. So this can be formulated in a great generality. So G is a quasi-split group. I've written classical because we are worrying about classical groups for now. Psi is an Arthur parameter. Phi psi is the Langlands parameter for psi. ABV packets generalize Arthur packets in the sense that the Arthur packet attached to psi is the ABV packet attached to phi psi. And in order to show this, we must show that the distributions, the virtual representations that we wrote down match with each other. So we can also write down a pure version of all of these statements. Okay, so what has been done? So great strides have been made in the Archimedean case by Adams, Arancibia, and Mezzo. So for classical groups, this is known. For unitary groups and strong real forms of real classical groups. For p-adic groups, along with Clifton Cunningham, we wrote a series of 2 papers that proves this for p-adic GLN. And there are some very nice combinatorial arguments that generalize a key combinatorial lemma that we used in our first paper, both by Chi-Heng Lo and Connor Riddleston, independent of each other. That, oh, no. Am I going back? No. Okay. All right, we're back. By Connor Riddleston and Chi-Heng Lo for GLN, that gives an alternate proof. For tempered irreducible representations for any connected p-adic group, the argument is in Cunningham, Dijoux, Fiori, and Zhang. And so what is the current status? So in collaboration with Cunningham, Hazeltine, Liu, Lo, and Xu, we are working on all the groups treated by Arthur in the paper in the 2013 paper. And for now, I'm able to state, let psi be an orthoparameter for split SO2n plus 1, assuming the twisted p-adic Kazhdan-Lusztig hypothesis for GL2n. Eta psi s Arthur is eta phi psi s ABV, and also their pure versions. And as a result, the local Arthur packet for psi is the ABV packet for phi sub psi. So this is part of a larger project where we do more. So we hope to include the other groups treated by Arthur. We need the p-adic version of the Kazhdan-Lusztig hypothesis for classical groups as well. So for SO2n plus 1, you see Solivel's article. And the hypothesis that we require, which is not proven, is a twisted p-adic Kazhdan-Lusztig hypothesis, and that is ongoing. Okay. So here are all the collaborators and 100% authentic photograph of all of us in the same place together. No. Okay, so maybe unfortunately there's a little bit more left. So just wanted to show you where the hypothesis shows up, and that is a good excuse to talk about one piece of the proof. So recall, right, so the main philosophy of the proof is to write down geometric versions of these transfer maps that Arthur has used to define local Arthur packets, and this is coming from ABV's original book. So for G equals SO2n plus 1, you can write down an Arthur parameter, and its infinitesimal parameter is lambda. So you can include that inside GL2n to get an infinitesimal parameter for a general linear group. And then you can sort of treat it as an infinitesimal parameter for this disconnected group. So this is, I'm only talking about this particular transfer map. So if we briefly focus our attention on this transfer map, so that's the slide for that. So we have this transfer map written in terms of Grothendieck groups. It's going from the Grothendieck group for G, like a particular important subspace of stable virtual representations of the Grothendieck group attached to G, to the Grothendieck group attached to this disconnected group for the infinitesimal parameter lambda plus. And we need to show that the transfer of the Arthur type virtual representation is equal to the ABV virtual representation. So in order to do that, because the virtual representation attached to the ABV packet is defined geometrically, we need to have an appropriate geometric version of this transfer map. And there is a sophisticated way to describe it geometrically, but it all boils down to the fact that if you take the transfer of a virtual representation and pair it with a perverse sheaf now attached to the disconnected group, GL2n semi-direct Z mod 2Z, that pairs with eta and a twist of the restriction of the perverse sheaf P. So on the left-hand side, the pairing is for GL2n semi-direct theta. And on the right-hand side, the pairing exists on SO2n plus 1. And the way we are geometrizing transfer is by realizing it in terms of some twist of restriction. And in order to prove this, we apply this restriction on the basis of standard objects, so standard sheaves. And we can understand that pretty quickly. However, we need to apply it to virtual representations written in terms of simples. And that is where we need the twisted version of the p-adic Kazhdan-Lusztig hypothesis. So that's where it shows up. So it allows us to go back and forth between the basis of simples and standards for G, and the twisted version does the same for the disconnected group. So why care about ABV packets? Well, it's completes the story. Geometric realization matches Arthur's results. Well, ABV packets are more generally defined for any Langlands parameter. And in fact, non-Arthur type ABV packets are pretty interesting because for GLN, both the L packets and A packets are singletons, but it has been shown by Cunningham, Fiori, and Kitt that for GL16, there is an ABV packet of size 2. And geometry is cool if you want to. So typically people provide a proof sketch, but I have nothing as sophisticated. So I have a proof cartoon, which is how it lives in my head. So just giving you a glimpse of all of the ingredients that will go to show that the twisted endoscopic transfer of the Arthur type virtual representation will match with the ABV counterpart. So for that, we actually need to start by writing appropriate virtual representations attached to the twisted GLN. And the Arthur type virtual representation matches with the ABV virtual representation because of our work for GLN. And we can write down Arthur's theory to match the transfer of eta psi Arthur to eta psi for twisted GLN. And on the right-hand side, we can reduce this pairing to a pairing on SO2n plus 1 by using a fixed point formula that vanishing cycles will satisfy. And finally, by using a geometrized version of transfer, this reduction is the same as the transfer of the ABV type virtual representation. And for step 4, we need to assume the p-adic Kaj-Dunn-Lustick hypothesis. So we wanted to show that these two things are equal, and going via these equations, we are able to do that. So I'm happy to answer more questions. This, I understand, was very vague, but thank you very much for listening to me. And here are some cats.